Hi everyone, today we will solve word search 2. The problem statement is that we are given a matrix of characters and we are given a bunch of words. So we have to search these words in this matrix like crossword, and whatever are the words that we are able to find, we will put them in a list and then return that as the output. So in this particular example, we have eat, E-A-T, and we have oath. Of these four words, we are able to find two, and that is the answer. Whereas in this example, what we need is A, B, C, B, and we are not able to find that. One thing is we can't go diagonally. The other thing is we cannot go back to an already visited character. So that is why we are not able to, this output is empty. So now let's go into the intuition. So the bottleneck for this problem, if we look at the constraints, right? So the length of the board itself is not much. It can be maximum 12 cross 12. And the length of each word also is going to be not much. Each word can be up to 10 characters long. But if we look at how many words we have to search, this is a big number. So this is where our bottleneck will be if we search one word at a time. So if we want to search a whole bunch of words, what is the data structure that we will use? We will use a trie data structure. Let me go to the visualization. So this is how our trie will look like once we build the trie using the words that are given in our input. Right. So here we have boxes, pin, pig, pie, rod, pit, and yak. So the prefix for pie, pig, pin, and pit are the same. So all of them fall into the same subtree. But this node has a word ending. These are the leaf nodes that obviously have a word ending. So how do we construct this trie? We will go to the code for a moment. We define a new class for having this trie node. So it is essentially a dictionary where the key is a character and the value is a trie node. So this is how the dictionary will look like. And we also have another member which is word. So this denotes whether a particular node is a word ending, and if it is so, the reference to the actual word is being stored here. So if you look at our visualization, right? So this is a word ending, this is a word ending, right? So in these nodes, the self.word will be pointing to whatever is the word string that we have in our array. Right? So this way we know that when we are traversing these nodes, we know whether it's a word ending or not. And if it is so, then we'll append the word to the list. Let's step into our algorithm. So what we do is we go over each of the cells here, and from each of it we will do a depth first search and see if we are able to find any of the words. So the first one will be like stepping into B. Now we are at the root now in the tree, and we are at the very first cell in the matrix. Now we are at B, so we see whether root node has the child B. It has the child B, so the tree will, traversal will go into B, and for B we will see if any of the neighbors are a children here. So we go here. So now we are in B in the trie, and we are in this B in the matrix. Now we have two neighbors that are visible. W is 1 and O is 1. Now we do have O here, and we do have the neighbor for B here. So we'll step into that. Right? So we are starting to form a word. Now we'll step into O, and this again has these three neighbors, but B is something that's well already visited, so we can't go back to this. So we'll see this P and X. So of these two, we have X there. So we are going to try and construct the word From X, we see the neighbors, that is W and R, but there is no child that is W or R here. So, this is a futile depth. So we are going back in the DFS, and then we are going to, check for W and again W and O, but none of those are a child in for the root. So only when we find a valid child, we are going to again traverse the trie. So we step into P, and then P has these 4 neighbors. Of these 4 neighbors, we have I. So we're going to step into I. For I, now we have identified a word ending here. See, one of the inputs is pi, and we identified a word ending. That means we have to add it to the result. Okay, so it is added to the result here. Now we take a step back. We go forward with pi, and then look at its neighbors, and we again found another node as its neighbors, n. So this word is formed, so we are going to add it to the result. And again, there is one more neighbor of this I, which is G. So that also will traverse and add it to the result. Now one of these is pit, but I does not have a neighbor that is T. So this word is not found. Right? So we are going to go back and see is there anything else that we have? So we have seen all of it. Now it goes back to the DFS. So it goes back to the root. And after that, we are going to find a character. We are going to keep traversing and see if we are able to find any child of the root in our matrix. After P, there is no child of the root that starts with I, Z, X, W, G, J. So we go straight to R, right? And we of course can find R, O, and D. So I'll just quickly go over these now that we have how this works. So this rod has been added to the result. And then we have yak, which would be the final word that we might want to, that might that we might come across, but I don't think there is any scope here, so our program is done. Right. So let's go to the code. We'll be able to understand, how it works. Okay, as we saw earlier, this is our trie node class. It is essentially a dictionary, and whether it is a word ending, if it is so, it's a reference to the word in the words list. So we initialize the root trie node, and then we construct the trie one word at a time. So we take one word, and then we take all the characters in the word one by one. And if the root already starts with that character, then we just traverse it. Otherwise, we create one, and we keep going. Making node as the child which we just created or which we just found, and then we keep going till this each child, this loop is done, and whatever is the last node, we make that as a word ending by assigning node.word equals the reference to the particular word that we just traversed. So this is how we build the trie. The next thing that we do is for each, so after that this is a DFS function, we'll come to it later. Now the next thing that we do is for each cell in the matrix, we do a DFS of that particular cell starting from the root. Okay, so now let's step into the DFS. Right. So what we do is we pick the character. So if it is 0, 0 here, we pick O and assign it to CH. Okay. And if we are not able to find it while we are traversing at the root first. If you are not able to find, nothing to do, we just return. Otherwise, we keep traversing by going like this. Next node equals node.children of CH. Okay. While we are doing that, if we find that it is a word ending, right? If we find that that particular node is a word ending, then we append it to the result. Okay. So otherwise, we keep going into our DFS in all 4 directions. But before we go into our DFS, we make the current character as hash. This is a proxy to mark that a particular character or a particular cell in the matrix is already visited. So after we do our, recursive DFS, we again mark the hash back to the original character. And this is like, we travel in all four directions and DFS if in case we find there is a match in the trie and the matrix neighbors, like how we saw. And, in the process, as we saw, like we are already like appending the results. So finally, after all the DFS is over, we return the result. So this is how this code works. Hope this was useful to you. See you in the next video. Thank you.